Hello, I am Anwoy and I am presenting our work titled Language Models Can Exploit Cross-Task In-Context Learning for Data-Scarce Novel Tasks. This work has been accepted at the main conference of ACL 24. It was done at LCS2 lab at IIT Delhi. In-context learning has been a very useful phenomena of LLMs. LLMs can perform tasks but by just seeing examples provided in context. For example, if we provide the LLM with the task definition of classifying a review as positive or negative, it can classify it just based on the task definition. Such a paradigm is called zero-shot prompting. In few-shot prompting, we give extra examples in context before providing the LLM with the input target example. For example, here the target is to get the sentiment for it was a very pleasing 3 hours review. But to enable the LLM to learn how to label a review, we can provide two examples of reviews within its context as shown here. But what if we don't have few short examples? Suppose there is a task shown here where it is a question from a scientific exam, here biology. Suppose I am a naive user, a non-expert, and it is very tough for me to create examples of biology if I don't know a subject. However, I am interested in knowing the answer to this. How will I query the LLM with in-context examples? For such tasks, can we use examples from other tasks which are more commonplace? This is the research question we are exploring. We call this cross-task prompting. For example, given the question of biology as shown in the previous slide, we can ask the question to the LLM giving examples in the context from other tasks, like for example as shown here we can take a source task bool q where the task is to classify a question, rather answer a question as true or false given a context. Can you use examples from such other tasks to solve a target task for which we do not have uh, demonstrations or examples? This is the research question we are exploring. We are exploring the potential for information sharing across tasks. Now, to emulate this novel task phenomena, we incorporate domain diversity and choose tasks which are deemed as difficult. For example, we take ARC challenge, which consists of hard natural science questions. We take financial phrase bank as one of our target tasks, which is domain specific, requires domain expertise, and is for financial sentiment analysis. We use questions from PG medical entrance exams called MADE MCQA, which also requires domain expertise. We use SciQ, which is scientific questioning dataset, and social IQA, which is a common sense reasoning dataset. These tasks are used as target tasks for our experiments. We choose these 5 target tasks. We take 10 source tasks, which consists of ARC Easy, AG News, Bull Q, Common Sense QA, a POS tagging task, a NER task, NLI task, QQP, RES, and SSC2, which are sentiment classification tasks. These source tasks are very common in NLP, like text classification or POS tagging or sentiment analysis, and we use examples from these source tasks in context to solve the target tasks. For the 5 target tasks we chose, the performance of the zero-shot performance of language models are very poor. For example, for Llama to 7 billion, the performance is consistently below 50%. For ARC challenge is somewhere close to 4%, and similarly for MedMCQ and SciQ. Though GPT 3.5 performs quite well even for zero shot on these target tasks, but our focus is mainly on smaller LLMs like 7 billion or 13 billion LLMs. If we use even one cross-task example in context, we see a remarkable performance boost of 107% on average. In fact, in the diagram shown here, in the chart shown here, we have shown the best performance with a source task, and we see 162% improvement. For example, for ARC challenge, common sense keyword serves as a best source task, and the performance boosts from 4% to approx 42%. Similarly, for financial phrase bank, mid MCQAs, IQ, and social IQ. For Llama to 13 billion, we see a performance improvement of 18.6%. And for GPT 3.5, where the zero shot performance was already very good, even then we see a performance boost of 3.2% on average and approx 7% for the best source task. Even with dissimilar source tasks, we see performance improvement. What do you mean by dissimilar source tasks? For example, the task boolq, MNLI, and QQP, which are Boolean question answering, NLI task, and natural understanding task, doesn't match with any of the 5 target tasks in their form or question patterns. Still, we see an average of 105.9% improvement with these 3 dissimilar source tasks averaged over the 5 target tasks. However, in traditional in-context learning, we see that the performance generally increases up to 8 shot and then stagnates. But in cross-task prompting, we see that the performance largely stagnates at 1 shot. Uh, in some scenarios it may be possible that we have or the user can create one or two in task example. But maybe creating examples like 8 for domain specific task is tough, so we saw the possibility of combining in task prompting with cross task prompting. And except for the dataset financial phrase bank, we saw that even by incorporating say for this in this case where 8 demonstrates 8 cross task example and 0 shows 8 in task example, the performance are largely the same. This is for Llama to 7 billion, this is for Llama to 13 billion, and this is for GPT-3. So we see that increase in cross-task examples gives a stable performance for all tasks except for financial phrase bank. Now we see that what can be an application of cross-task prompting. Suppose we have a small unlabeled data set for a given target task. So we cannot incorporate these examples into the context because the dataset is unlabeled. Can I use cross-task prompting to generate pseudo-labels for this unlabeled dataset? So what we did was we took a small unlabeled dataset. We used cross-task prompting using those 10 source tasks, generated pseudo-labels using one example from each source task in the context, and then did majority voting. And whatever whatever label was generated by most of the source tasks is then chosen as a pseudo-label. We then use this pseudo-labeled example in the context of the target task and see the performance. We see that using the gold label and using this pseudo label generated by crosstask actually gives almost similar performance in all cases, bearing one or two. Uh, if we use pseudo label generated by zero shot prompting, the performance is substantially low. So the pseudo label generated via crosstask prompting actually lead to comparable performance as gold label. So this can be a very interesting use case of crosstask prompting. Now we analyze what can be an ideal source task. We take the cosine similarity between the final layer hidden states corresponding to the source task and the target task definition. We observe that, as our intuition suggests, 80% of the time the source task definition, which is most similar to the target task, give the most improvement. That is what is shown in this heat map. We then study the layer-wise correlation between the hidden state embeddings of the source task definition and the target task definition, and calculate the Spearman's coefficient, Pearson's coefficient, and Kendall's tau between the cosine similarity ranking and the uh, performance improvement rankings of the source task. What we see is a U-shaped pattern. This indicates that in the initial layers of the model, there is more task-specific computation going on, whereas in the latter layers, actually, this cross-task information sharing is happening. So what are some of the takeaways? So we conclude that LLMs can substantially enhance their performance in novel task scenarios, even when direct examples from target tasks are lacking using cross-task prompting. So this is it unveils a fresh possibility that how can we integrate LLMs across a broader spectrum of applications and adapt them to novel tasks at inference time. The possibility of generating pseudo-labels and using the pseudo-labels examples in context can be a viable solution for situations where annotated data is scarce. And from the interpretability analysis, we saw that cross-task signal transfer is abrupt and happens at the latter layers. For the future work directions, one is automating the best source task selection for a given target input, and of course we need a deeper understanding that how this task information is captured inside the LLMs through the studying interpretability paradigms like mechanistic interpretability and looking at the circuits facilitating cross-task prompting inside LLMs. Thank you.